This is part 3 of our presentation on direct lookahead approximations. Here we're going to do stochastic lookaheads, and we're going to deal with the policy within the policy and illustrate different types of policies. So here we are at part 3. We're going to talk about PFAs, CFAs, and VFAs for the policy within a policy. Okay, let's start off with a PFA-based lookahead. Inventory planning problems, real world ones, are really fairly complicated. Often we have very long lead times. We have to think well into the future. Lots of uncertainties come up. Let's imagine the problem faced by a candy company that's planning over 12 months, and they have this big spike in the United States called Halloween. And Halloween, the demand is so high that you have to plan into the future because they don't have the production capacity. So if they do this, the production, a planning model, say a deterministic planning model, might look forward and say, okay, we have to optimize production by creating product well in advance of the holiday. I can't just wait for the holiday. So this is screaming to be done as a direct look ahead. But let's say I don't want to do a deterministic look ahead. I want to handle uncertainty. So we're going to go back to our stochastic look ahead. We're going to use our notation of the tildes. The challenge here is coming up with the policy within the policy. So I know that to make my decision in January, February, March, I need a look ahead policy that will look out to Halloween. But as I look ahead, I need to model the fact that I'm still making decisions. So I'm not going to implement those decisions, but I need it to make my look ahead model more realistic. So here I want to design what those policies should be. That's the policy within the policy. Let's imagine that we say, okay, I'm going to use a classical inventory policy called the SS policy, or order up to. I'm going to use my theta notation of theta min and theta max. If the inventory goes below theta min, I have to order up to theta max. So again, remember, this is just an approximation to help us make decisions in the future. But it's a simple PFA policy. What we're going to do is we're going to start with our optimal policy. That's the top line. Notice no tildes. That's our original statement of the optimal policy. We then go to our approximate look ahead. Now we've got the model with all the tildes all over the place. Variables have double time indices other than time t. Okay, so we have S tilde t prime for t prime starting at t plus 1 and so on. Now we've got that max over pi tildes. That's the policy within the policy that we have to design. So this is going to be the focus. All right, here we're going to start that top line. That's our approximate look ahead with all the tildes. Now we're going to substitute in our parameterized policy. Now our parameterized policy, our order up to policy, once you fix the type of policy, now I'm just down to choosing the parameters. That is the order, the reorder point and the order up to. I'm going to call those theta min and theta max. Now, because of that, I'm going to max, instead of over the policies, I'm going to max over the thetas, the tunable parameters. Now, that doesn't look that attractive either. That's not easy because that's a maximization inside an expectation, which means, so inside the expectation means, so I started at time t in state st, I made a decision xt, then I observed something random, and that took me to time t plus 1 and the state S tilde t plus 1. That means when I do that max, technically, I'm going to get an optimal theta that's a function of S tilde t comma t plus 1. I have to admit, that looks really ugly. I'm not going to sit there and do a maximization problem for every possible value of the future state. So what we're going to do is another approximation. We're just going to replace it with a constant. Now, because we're replacing it with a constant that's not only not a function of the state, it's also not a function of t, I can now bring that constant all the way out front. You see that in the third line, where now it's embedded in the policy itself. Now it's a parameterized policy, assuming that I've given that the policy within the policy is an order up to policy. Okay, so we're starting with that order up to policy, replacing it with a parameterized policy, parameterized by theta tilde. And then we're coming down and we've got a policy that's just a function of a fixed parameter theta. Okay, so here our order up to policy is now embedded, that's the policy, the X tilde policy embedded in the look ahead. Notice that we no longer have a max operator. So the max operator is gone because I said, oh, I'm just going to use some constant that's fixed in advance. And so now I've got that parameterization theta in the policy itself, in the look ahead policy. Okay, so now I'm back in the world of a classical basic parameterized look ahead policy. Now, my x sub t is a scalar, so I can loop over all possible values, 0, 1, 2, 3. Later, we're going to consider more complex problems, but for now, I can just loop over all the x's. And for each x, I have to simulate it using a fixed value of theta. Now what I've got is a basic stochastic search problem, and I can do derivative-based or derivative-free. Now my forward simulation, I am going to get a random observation, so I'll have to deal with the noise, and we'll come back to this later. This is what we're going to eventually call an optimal learning problem, also known as a multivariate bandit problem. But we can loop over the x's. I can do one or a number of future simulations and take the average, and then based on that, just pick whatever x seems to work the best. Now, let's build all of that into my look-ahead policy. So here I am at time t. I'm going to loop over all the x's for each value of x for a given theta. I'm going to simulate into the future. Now, I haven't yet optimized my theta. Let's just assume I'm given a theta. My policy will be a look-ahead. I've got that stochastic simulation, and all of this boils down to choose the best xt. Then I roll forward and do it all over again for xt plus 1 and then xt plus 2. So now we've seen that this is all a giant look-ahead using a simplified order up to policy within the look-ahead model. Okay, let's now consider a CFA-based policy. I'm going to take a problem of dynamically routing over a graph. Here's my shortest path problem. By the way, this is a real-world situation. I'm actually up in Hartford, Connecticut, working with a company. It's 4 o'clock in the afternoon. I need to get back to my home in Princeton in the bottom left-hand corner. And at 4 p.m., it's got a path that's going to put me right in New York City at 5 p.m. So, of course, the uncertainty of going through New York at 5 p.m. is a challenge. Now, let's assume I've got a static deterministic network, obviously much bigger than this little graph, but whatever. This will be our stand-in image for the deterministic lookahead that Google's actually using. And it will have point estimates of all the travel times. Now, what I can do is instead of using the point estimates, I could use a theta percentile, like an 80th percentile. This is because I'm worried about the upper tail. I'm worried about the worst case, clearly the worst case of going through New York City. But once you've fixed percentile, which is parameterized by theta, which is it the 70th percentile or the 80th or 90th, I still have a number of fixed costs. So I still have a deterministic graph, and I can solve a standard deterministic shortest path problem. So this is just a modified deterministic shortest path problem where all the costs have been replaced with the theta percentile. Okay, so here we take our graph, we look forward. Again, all the travel times in there are no longer the point estimates. They're now some percentile, and those are very easy to compute. I mean, even Google would be able to do that on a large scale. Now, I'm going to use my theta percentile graph, use it as a look ahead, and as I step forward through the graph, as traffic conditions change, I'll keep updating and solving this modified shortest path problem. So this is now a policy where the policy is to solve a modified deterministic shortest path problem. For a given value of the percentile theta, you're going to simulate it. I can simulate over time following a sample path. Obviously, I'd like to be able to do that many times to take an average. My stochastic optimization is how do I do the parameterization? So I've chosen to do the theta percentile. I could chosen other ways. That's the choice of F. And then now I have the tuning of theta. Now, theta here is just a scalar. I can try different values of theta. Here, we've done a number of simulations. If I'm minimizing the expected cost, it turns out that the optimal theta really is the 50th percentile, okay? But let's say I actually need to get home for dinner and I really don't want to arrive late. and I want to minimize the probability of arrival late. This is a different objective function, but with that different objective function, the optimal theta comes out to be 0.8. And so if I'm just trying to minimize averages, it may be not a big surprise that theta equal to 0.5 was the optimal parameterization, but once you put in the risk arriving late, I want something that's more conservative. So finally, a VFA-based policy. Okay, so we've already seen that VFA using value function approximations is fairly complicated. I'm going to actually use a real-world problem where we really do a look ahead using VFAs, but I'm not going to get into the math. I'm simply going to sketch the problem. It's one of our problems in fleet management that we do at Optimal Dynamics. Let's imagine the problem is that I have a load of freight on Friday, but today is Monday, and I have to say yes or no to that load of freight moving 4 days in the future. So 4 days in the future, truckload movements typically take a day or two. Sometimes the longer movements are 3 or 4 days. By the time you're getting 3, 4, and 5 days in the future, truckload carriers don't know what freight they're moving. They don't know where their drivers are going to be. It's highly uncertain. My decision here is not to dispatch drivers. My decision is to say yes or no to this load of freight that some shipper has said, hey, I need somebody to move my load of freight on Friday, 4 days in the future. Okay, and this is how truckload trucking actually works. So I have to be able to say, do I think I'm going to have a driver able to pick up that load in the future? Now, what we're going to do is use approximate dynamic programming that we've developed for fleets of trucks. This is a generalization of my pneumatic truck problem, but instead of one truck, we can handle 100 or 1,000 trucks. And we're assigning trucks back there on day one. Those curves are the value of having 1, 2, 3, 4, 5 trucks in the future. Those are value function approximations. So we're using approximate dynamic programming to approximate the value of drivers in the future. We're using the VFAs to help with dispatching drivers, and we are going to simulate the dispatching of drivers. So given the VFAs, we're going to walk into the future running a simulation. Now, as I step forward, I'm following one sample path. We're going to do this many times. I may do it 10 or 20 times and then start taking averages. So let's imagine that I'm going to do 20 simulations. I'm going to take 20 samples. And for every load in the future, I'm going to ask for each sample, did I cover the load? Yes or no, 0 or 1. So if load 001, I might say, wow, I've done 20 samples, 20 simulations in the future, and that load was covered 18 out of 20 times, so it has a 0.9 probability. Load 002 was covered 14 out of 20 times, so it has a 0.7 probability. And load 003, we covered him 19 out of 20 times. So we have an estimated dispatch probability of a coverage probability of 0.95. Now, what you have to do is evaluate this look-ahead policy. It's a look-ahead policy, so this is a DLA. The look-ahead policy, not only am I accepting loads, I do have to dispatch trucks. We are using VFAs to dispatch the trucks. Now, I can simulate the DLA policy by saying, hey, I'm going to do 20 simulations at time t, roll forward, do it all over again at time t plus 1, t plus 2, and so on. So this is a rolling horizon of a DLA policy. The DLA policy is using VFAs to create a dispatch policy within the look-ahead policy. Now, we did this on a real problem. We had about a little over 10,000 loads. And it turned out after we did the full simulations, 5,000 loads we just never covered. They were just like, no, these loads are just completely impossible. 3,280 of the loads we covered 100% of the time. They're just no-brainers. Absolutely, yes, we'll do it. And then we've got about 3,000 loads in between where the probability coverage was anywhere from 1 out of 20 to 19 out of 20. Now, what I'm going to have to do is come up with some rule. I'm going to come up with a rule of like 0.8. If I can cover that load with a probability greater than 0.8, I'm going to say yes to the load. That rule of greater than 0.8, that's a PFA. So you can see that we're doing a mixture of PFAs, we got VFAs within our DLAs, but you have to be, in real world problems, you've got to have the full toolbox. Okay, so more on policies, go to policies and click on direct look ahead approximations.